As we turn the page over in our lesson, we see that we have an example, a word problem example, that says that Vitaly and Sherry have 24 meters of fencing to enclose a rectangular garden at the back of their house. They want us to express the area of the garden as a function of its width and to determine the domain and range of the area function. Well, we can do this. We can say that the garden itself looks like this. Here's our width, and here's our width, and here's our length. We don't need to use any fencing along the back because it's up against the house. So we know that these three sides added together will equal 24. So W plus L plus W will equal 24. Isolating for L, we see that L is 24 minus 2W. Now we can come up with an area formula. Area of a rectangle is equal to length times width. So we can say that the area of our area function in terms of W, and mathematically we write it this way, our area function in terms of W is length, which is 24 minus 2W, times W. Okay, so we'll say that one more time. The area of this rectangle is equal to length times width. But we've already established that length is 24 minus 2W. So in other words, the area is 24 minus 2W times width. And because we only have one variable now, W, we can say mathematically that area in terms of W is 24 minus 2W times W. This is a new type of notation that we'll talk about soon. And so now what we've done is we've expressed the area of the garden as a function of its width. Right there. Next thing we're going to do is determine the domain and range of the area function. Well, just looking at it, we can see that if we were to have the maximum possible length, that would coincide with there being, if we were to have the maximum possible width, that would coincide with there being the minimum possible length. So in other words, if we drew a really strange looking rectangle that looked like this, with as long a width as possible, and as long a width as possible, and just a little tiny length right here, we could say that theoretically at least this little tiny length will let it be 0, and what that'll do is that'll maximize our widths for us. So that's what we do. We let the length equal 0. In other words, 24 minus 2W equals 0, because we established earlier that the length is 24 minus 2W. Letting 24 minus 2W equals 0 means that W equals 12. So the highest possible width value we could have is 12. We could have 12, 0, and 12, and that would use up all 24 meters. Now in terms of the range, we have to determine all the possible values of the independent variable. And that's actually relatively easy to do because in terms of the range, we want to find all the possible values of the dependent variable. And that's actually kind of easy to do because we can recognize that what we have here is a parabola. This is just an upside down opening parabola, 24 minus 2W times W. And so we can say that if I was to partial factor this, it would help me to find the vertex of that upside down opening parabola. So why don't I let the y value equal 0 and partial factor? 0 equals 24 minus 2W times W. Setting this factor equal to 0 gives us W equals 12. Setting this factor equal to 0 gives us W equals 0. Our axis of symmetry is therefore at 12 plus 0 over 2, which is 6. Now we know that we've got a parabola opening downwards with a vertex at x value, or in this case W value, of 6. That means that the maximum possible value for y will occur when the W value is 6. Letting W equal 6, we see that the area would be 24 minus 2 times 6, which is 12, times 6, which is 72. So what that tells us is the following. When the area is at its greatest, in other words, the vertex, the W value is 6, and subbing in for y, or in this case a, we get a maximum a value of 72. So in other words, the vertex is at 672. And that allows us to say that the range is equal to the set of all y such that 0 is less than or equal to y is less than or equal to 72, and y is an element of the reals. Okay. Final question in this little lesson says the CN Tower has a lookout level that is 346 meters above the ground. A gull lands on the guardrail and causes a pebble to fall off the edge. The speed of the pebble as it falls to the ground is a function of how far it's fallen, and the equation is given by this. The velocity in terms of the distance is equal to the square root of 2gd. This is a what's called function notation form, and we'll go into that in depth shortly. So we've got d is the distance in meters the pebble's fallen, our independent variable. V of d is like y, that's our dependent variable, and g is a constant. What we want to do is determine the domain and range of the function v of d. In other words, determine the domain and range. So right away we know that the minimum value of d is 0, because d refers to the distance that the pebble's fallen off the ledge. So right at the start, the pebble is, at the instant the pebble drops, it's still 0 meters away from the edge. And the maximum value it can fall from the edge is 346, because it's 346 meters above the ground, and when it hits the ground, that'll be the greatest possible value for d. So our domain is the set of all d such that 0 is less than or equal to d is less than or equal to 346, and d is an element of the real numbers. Now, our minimum velocity will occur when d is equal to 0. When d is equal to 0 and the pebble is just first falling, the speed it's falling is at a minimum. Well, v at 0 is equal to the square root of 2 times 9.8 times 0, which is 0. The maximum possible velocity will be at the instant it hits the ground. And at that moment, d is equal to 346. Well, v at 346 is equal to the square root of 2 times 9.8 times 346. And that's approximately equal to 82.4. And so we see that the minimum possible speed is 0, the maximum possible speed is 82.4. And so we say that the range is a set of all y such that 0 is less than or equal to y, less than or equal to 82.4, and y is an element of the real numbers.